Okay, so this for this force video, what I want to look at is there's a little less math than the inclines, but just kind of some things with when we're talking about resultants, which is really just another word for net force. So if you have various forces acting on an object and it's not moving, well then you know your net force is zero. But if it is moving, then the resultant is what you're kind of looking at, in other words, you've got, force here, and what is the result of that? And so let's kind of look at some of the math involved with that. So this first question, this is one of I have a little trick that I do with this, which you may or may not want to use, but the diagram below represents two concurrent forces. So I have something going left on the horizontal and straight up on the vertical. And then we want to find out which vector below represents the force that will produce equilibrium with these two forces. And what that's asking is, so I have a force going left, I have a force going up. What kind of force would I be required on this point that you're dealing with to cause it to stop? Equilibrium means that it's not really going to be moving at that point. So what I would like to do in this case is I want to take a point. I'm going to take one of my arrows and I'm going to point it in this direction. That's that horizontal force right up there. And then I'm going to kind of change this. Instead of putting the vectors as tail to tail, I'm going to put them as the arrows to have them touch. So when I do that, this represents, let's say this is A and this is B, and now we have A and we have B. And if you think about it, if you have two things that are coming in at this angle, what's going to happen is they're going to push off in this direction. And so in order for this to produce equilibrium, in order to get this to stop, I would need something to come in this direction with an equal force of what I have here. So that makes it a little bit simpler to kind of calculate this problem. Number 3 there would make the most sense in that case. Number 9, whenever I see these resultant problems where I have force going in one direction, force going another, I'm always thinking in a Pythagorean. There's got to be some kind of, a squared plus b squared equals c squared type question in there somewhere. And so let's take a look at this one. In the diagram below, a 20 Newton force due north and a 20 Newton force due east act concurrently on an object. So one of them is pushing the object in this direction, one is pushing in this direction, and as shown on the diagram below, the additional force necessary to bring the object into a state of equilibrium is, now what that's asking is, we're going to figure out which direction is this object going with a northerly force and an easterly force, and then what do we need to do to stop it? So again, I'm going to do my little trick with the arrows. This is my north force, and then this is my east force. And so I'm pretty sure that the object is being forced up in that direction. And so what I want is something that goes this way. So I want something that goes south and west. So I know I need a southwest force. So that means it's either this answer or this answer. And now I need to do the math on it. And because I have something here that's going due north, due east, I know that I have a 90-degree angle in there. We can use Pythagorean, and we can say, well, I have 20 squared plus 20 squared square root thereof equals 28. So my answer has to be 28 newtons to the southwest. Okay, and it's southwest because remember, this is being forced to the up and over, so that's to the northwest. So if I want something the opposite of that, I need to go in this direction. Let's try this one here. Two forces, F1 and F2, are applied to a block on a frictionless horizontal surface. So remember, in physics land, very often surfaces are frictionless. So I have something going in this direction that's 2 newtons. I have something going in this direction that's 12 newtons. Obviously, a 12 Newton force in this direction would be able to overcome the 2 Newton force in that direction. And so they're saying if the magnitude of the block's acceleration is 2 newtons, what is the mass of the block? And so I'm going to say, well, I know that my net force would be 12 newtons minus 2 newtons would be 10 newtons, probably negative 10 newtons actually. But magnitude, we can get rid of the negative sign there. So 10 newtons is going to be equal to mass times acceleration. It tells us our acceleration is 2 meters per second. So 10 equal to some mass, unknown mass, divided by 2 is equal to 5. Okay. All right. Number 12 is asking us on the diagram below, draw an arrow to represent the direction of the net force on the ball when it is at position X. And what has happened here, this is just sort of a projectile motion question. I have a soccer ball that's kicked from point P at an angle above the horizontal field. So we just got this nice parabola here. And then you have 2 different points. You have X and Y. And so with this, we want to draw an arrow that represents the direction of the net force on the ball when it is at position X. So right here. And then 13 is asking about the force, the acceleration of the ball at labeled at position Y. Okay. Well, remember that the force is essentially just force is equal to mass times acceleration. The ball's mass is not going to change. So really in this case, force will do whatever acceleration is doing. So it is true the ball is being kicked upwards, and so it's slowing down as it goes up, and then it'll kind of speed up as it goes down in the vertical direction. Horizontally, it pretty much stays the same all the way, but there's only one type of acceleration working on anything while it's in the air, and that's the acceleration of gravity. Okay, and so when it asks for the direction of the net force is going to follow the direction of gravity. So that's my answer to that right there. On the diagram above, draw an arrow to represent the direction of acceleration of the ball at position Y. It's exactly the same as force, because force, again, is controlled by gravity, and the mass of the ball does not change. So both of these would just be having your net direction would be straight down towards gravity. Now, I'm going to do this last one because it's just a little tiny bit weird. So when we're looking at these, we're saying, okay, a 5 Newton force could have a perpendicular components of, and we're trying to figure out, well, which of these would work for a 5 Newton force. So let's see, I would have to have something going in this direction, and I would have something going in this direction, which would give me something here that equals 5. Okay, and so really, if you think about it, in this case, I'm saying that I have C2, right, which is 25, and then at that point, I know that the square root of whatever I have has to equal A squared and B squared, so I just have to take these two and see if I can get the two of them to equal 25. So this would be 1 squared plus 4 squared would equal 17. This would be 4 and 3, or 2 and 3 rather, so 4 plus 9, this would be 13. This would be 9 plus 16. Oh, look, 9 plus 16. I believe that equals 25. And this would be 25 and 25. So this is more just thinking about the fact that we're doing Pythagorean every time. Now the reason it's this answer is, if I know that I have perpendicular components, I'm going to be putting it into Pythagorean. I'm going to do 3 squared plus 4 squared is equal to 20, well actually equal to 5 squared. Okay, and this one actually works, the rest of them don't work. So, all right, that should give you sort of a basic idea of force. Now there's a few other things we have to add to it, like tension, and then we have to add friction, but those will come in a different video.